last class we were discussing the possibility where the universe is filled with a constituent that has got pressure. We had started off by discussing the situation where the universe is filled with radiation. We know that radiation is photons, a gas of photons, and we had considered a gas of photons moving randomly in all directions and worked out the pressure for such a situation. The pressure also comes up, for example, when we have neutrinos, massless neutrinos, as one of the constituents of the universe, and there are variety of other possibilities which necessitate for us to consider pressure, the constituent of the universe having pressure. So, what are the effects, what are the consequences of there being pressure in the constituent of the universe? So, think of the universe being made up of, filled with some material which has both energy density, which we can write as in terms of some effective mass density, and a pressure. Well, the first consequence is that the equation, the gravitational equation, gets modified. Now, in Newtonian theory, the acceleration on a test particle, that is the thing that we were interested in, is just the mass in a spherical inside a sphere on whose surface the test particle lies, divided by r square and the gravitational constant g, which you can write as minus 4/3 pi g rho into the vector r. Now, once you have significant pressure, the Newtonian theory no longer gives you the correct answer. You have to incorporate Einstein's general theory of relativity, and the same equation now reads this. So, instead of rho, we have to use rho plus 3 p by c squared. So, this is the first change that arises when there is pressure. If there was no pressure, we would have this term, which is the familiar Newtonian situation. And we were considering a general situation where the pressure is related to the energy density through this equation of state, and the equation of state is quantified in terms of this parameter W, which tells us the ratio of the pressure to the energy density. So, we can so from here we went to a co-moving system, coordinate system, where we have the scale factor, and you can cast this equation for the scale factor in terms of this parameter W. Now, it does not suffice if we consider just one constituent of the universe, a universe with just one constituent. It is necessary to consider the possibility where there are different kinds of constituents, all of which have different equations of state, different densities. So, this equation takes into account the fact that there could be different possible constituents labeled by index I equal to 1, 2, 3, 4, which refers to different constituents of the universe. And as the universe expands, the density of each constituent of the universe varies with the scale factor. So, with increasing scale factor, the density is going to change, not as rho a cube being a constant. If it was just the usual matter without pressure, we know that rho into a cube should be a constant, because as the universe expands, the mass is conserved and a cube is the volume. So, if the volume increases, the mass density has to fall appropriately. But now we have to take into account the conservation of energy, and if there is pressure, the pressure will do work if there is expansion, and the conservation of energy leads us to rho I into the scale factor to the power of 3 plus Wi is equal to a constant, and we write that constant as rho I naught, the present value of the density of this particular constituent, and the scale factor at present is taken to be 1. Otherwise, we would have had the value of the scale factor to this power at present, but that has been taken to be 1. So, the universe may have a variety of components, a variety of superposition of variety of constituents. There could be 3, 4, 5 different components of matter in the universe. Each one is going to be labeled by 1, 2, 3, 4, etc. They are going to be labeled by this index I. So, we wanted to solve these two equations together, and the way we proceed is exactly the same as we did when there was only matter which has no pressure. We proceed in exactly the same way. There are two unknowns functions of time here, rho I and the scale factor A. So, we first replace this rho I and write it in terms of the scale factor and the present value of that density. So, doing that, we can write it like this, rho I naught into a to the power minus 3 into 1 plus w I. The next step is to multiply both the left and right hand side by a dot. Multiplying the left and right hand side by a dot, the left hand side we can write as half into the time derivative of a dot square. You can easily see that if I differentiate a dot square, I get a dot into a double dot into 2, which is cancelled out by this half. So, this term is exactly equal to this. Now, we want to write this term. There is a factor of a over here. There is a to the power minus 3 into 1 plus w I over here, and there is a dot over here. We want to write the combination of this, this and this, which are the only three terms which are functions of t in this expression. We want to write this combination as a total derivative of some function of a, and this can be written as the time derivative, sorry, this will be plus of a to the power minus 3 1 plus w I plus 2 into rho I naught. So, when I differentiate this exponent over here is essentially minus 3 w I plus 1. So, when I differentiate this term, I will get this minus 3 w I plus 1, and the power of a will go down by 1. So, here I have minus 3 into 1 plus w I plus 2, it will become plus 1. So, I have this 1 here and I have this term here, and I will get a factor of a dot. So, it is quite clear that when we differentiate this term, we recover this expression. You can check this little bit of algebra, that when you differentiate this term over here, you recover exactly this expression. So, both the left hand side and the right hand side are first derivatives of some function of time. So, we can integrate both the left hand and right hand side, and what we get is half a dot square is equal to 4/3 pi g, and now we have the sum over I rho I naught a to the power minus 3 into 1 plus Wi into a square, or plus 2, I can write it as plus 2 here, plus, so I have integrated this, I have integrated this. Now, when I integrate both the left hand and the right hand side, I can also have a constant of integration, which for reasons I had explained to you earlier, we can write as A, and we can interpret this as the energy of the test particle whose equation of motion we have written. So, we have in a fashion exactly analogous to what we had done earlier when there was no pressure, we have proceeded in exactly the same way, and we have integrated the second order differential equation for the scale factor and obtained a first order differential equation for the scale factor. Now, let us consider this equation. This is the equation that we obtain by integrating this equation once. This is a first order differential equation. Now, it is convenient to write this equation in a slightly different way. So, let me do that. To write it in a slightly different way, we multiply it by 2 throughout. So, we multiply it by 2 throughout, that is the first thing that we do, and then we divide it by a square throughout. So, if I multiply by 2 and divide by a square, the equation that we arrive at is a dot square by a square is equal to 8 by 3 pi g, and then we have the sum over I. Now, if I multiply it by a square, this, if I divide, sorry, I am going to divide it by a square. So, if I divide this by a square, I have a dot square by a square, that is right. I have divided it by a square. So, this power of plus 2 is gone. Rho I a to the power of minus 3 into 1 plus W I, rho I naught into A I to the power of minus 3 plus 1 plus into minus 3 1 plus W I is basically this divided by this, which gives me the density rho I at any instant of time. So, if I divide this by a square, what remains is this, and this I can write as rho I plus 2 E by a squared. Remember, we have multiplied this by 2 and divided it by a square. So, this constant gets multiplied by 2 and divided by a squared. Now, the left hand side, the term on the left hand side is nothing but the Hubble parameter squared. On the right hand side, we have one contribution from the densities of the different components of the universe. So, at any instant of time, we have one contribution from the densities of the different constituents of the universe, and we have a contribution from this constant of integration. Now, it is convenient in for many purposes to think of this particular constituent of the universe as another, to think of this constant of integration divided by a square, 2 multiplied by 2 and divided by a square. It is convenient to think of this as a fictitious additional constituent, as a fictitious as a fictitious component of the universe and this fictitious component of the universe is called the curvature component. So, bear in mind that this is a constant of integration that comes about. This term is a E is a constant of integration that comes about when we integrate a first order differential equation. It is convenient to think of it as an extra component of the universe. So, it is convenient to think of this as an extra component of the universe, and this is this additional component we shall refer to as the curvature. The reason why we refer to this as curvature I shall come to in later lectures. The reason is that when we interpret this whole thing in Einstein's theory of relativity, this term over here is related, this term over here is related, this term is related to the curvature of the space, spatial section. So, this term is related to the curvature of space. So, if I interpret this whole thing in Einstein's theory of relativity, the term that arises from the constant of integration is related to the curvature of space. So, we will think of this as an extra fictitious component of the universe. We have all the real components of the universe in this. We will think of this as an extra fictitious component, and we shall refer to this extra component as the curvature component, and the curvature component is denoted by the symbol k. We shall denote it by the symbol k. So, this term 2e by a square we shall write as 8 pi g by 3 rho curvature. So, we are going to interpret this term as a fictitious component of the universe, the curvature component, and we are going to interpret it, we have represented it as 8 pi g by 3 into the density of this fictitious component, the curvature. Now, there is a factor of a to the power minus 2. So, from this what we can say is that rho curvature into a square is a constant, rho the present value of the curvature density. So, this rho curvature with the expansion of the universe, its density falls as a to the power minus 2. So, obviously, this fictitious component, the curvature, does not behave like the usual matter. For usual matter it should fall as a cube, it falls slower than that with the expansion of the universe. So, we may ask the question, if I want to interpret this as some kind of matter with pressure, I want to interpret the curvature component as some kind of matter with pressure, and with the expansion of the universe its density falls as a square, then what should be the value of this equation of state parameter W so that this condition is satisfied. So, we want 3 into 1 plus W to be 2. If 3 into 1 plus W, so we would like for curvature 3 into 1 plus W curvature, this should be equal to 2, because we want the curvature component to satisfy this relation, because that is the term that occurs over here. It has a 1 by a squared. Now, if you want this condition to be satisfied, it tells us that W curvature should be minus 1/3. So, for this curvature component, the pressure is equal to minus 1/3 rho curvature naught into c square. This is just a fictitious component that we have introduced, an extra component which incorporates this term that arises from the constant of integration. Now, bear in mind that the constant of integration E can be can be either positive, negative or 0. So, what we see is that unlike any real physical constituent of the universe, component of the universe, whose density is necessarily positive, this fictitious constituent, the curvature, can have a negative density also. The negative density is allowed because this is not really a constituent of the universe, it is just a way of parametrizing this constant of integration that appears in our equation. So, if we incorporate this into this term as an extra component, we can write this whole thing as 8 pi g by 3 into sum over I rho I. So, we have this expression for the Hubble parameter, it is 8/3 pi g by 3 into the sum of all the densities of the different components in the universe plus the contribution from the curvature component also, that has now been included as an extra component in the density. So, we have this very simple equation for the Hubble parameter which governs the expansion of the universe. Now, it is convenient to rewrite this equation in terms of slightly different parameters. We know that the critical density of the universe is 3 h square by 8 pi g. So, at any instant of time, the expansion rate of the universe defines a density called the critical density, and the present value of the critical density is h naught square 3 h naught square by 8 pi g. So, what we do is we replace this factor of 8 pi g by 3 in terms of the critical density at present and the Hubble parameter at present. So, what this gives us is h square t is equal to so here we have replaced 8 pi g by 3 with h naught square divided by rho critical naught. So, we have h naught square and the sum of rho I by rho critical naught. Now, finally, what we can do is we can write this density in terms of its present value. So, doing that, so if we write the density of any component at some arbitrary time in terms of its present value, we have to scale it with a to the power minus 3 into 1 plus wi divided by rho critical naught. Now, recollect that we had defined the density of matter divided by the density of the with the critical density. At present we had, so let me remind you of this definition. We had defined the density divided by the critical density as the cosmological parameter omega. It tells you what fraction of the critical density is actually there in the universe. Now, we can do it in a situation where there are different components. So, if there are different components in the universe, the density of that particular component divided by the critical density is the density parameter of that particular component. This can be done at any instant of time. Now, we can apply this at the present value, at the present instant of time, at the present epoch. So, this gives us the value of the critical density at present. So, for each component we can use the ratio of that density of that component to the present. So, the present density of that component divided by the present value of the critical density, this ratio is the cosmological parameter corresponding to that particular component at present. So, it is the present value of the cosmological parameter corresponding to that component. That tells us that what fraction of the critical density is there in that component at present. So, we can use this definition here and write the Hubble parameter, the equation for the Hubble parameter at any instant of time as h naught square into this sum. This ratio is omega I naught, and then we have a to the power of minus 3 1 plus Wi. Now, let us spend a few minutes and just try to understand what this equation is all about. This equation has the complete information about the expansion history of the universe. By expansion history of the universe, we mean the Hubble parameter as a function of time. Once you know the Hubble parameter as a function of time, you can also determine the scale factor as a function of time. So, this equation has the entire information about the expansion history of the universe. It is a very important equation that we shall be referring to again and again. This equation tells you the expansion history of the universe in terms of presently observable or presently quantities defined at the present epoch. Let me repeat, this equation tells you the expansion history of the universe, tells you Hubble's parameter as a function of time in terms of quantities all defined at present. H naught is the present value of the Hubble parameter, omega I naught are the density parameters, present values of the density parameters for the different components of the universe. So, omega I naught are the present value of the density parameters for the different components of the universe, density parameter for the different components of the universe. So, the expansion history is given in terms of the present value of the Hubble parameter and the present value of the density parameters. Now, if I take this equation and apply it at the present epoch, the left hand side is h naught square, the right hand side also has h naught square into this. H naught square cancels out from both, the scale factor at present is 1. So, it leads us to this requirement that omega I naught is equal to 1. So, these two together, these two equations together tell you the complete information about the expansion history of our universe. Now, recollect, how did we get this? How did we get the fact that the sum of all the density parameters should be equal to 1? To understand this, to get a clear picture of where this comes from, let us go back here again. The Hubble parameter square is equal to this contribution from all the densities plus this constant of integration. Remember that we have incorporated this constant of integration as an extra constituent of the universe. And it is this fact that we have incorporated the constant of integration as an extra constituent which leads us to this. So, the curvature or the constant of integration has been incorporated as an extra component that comes into this. So, these two together are the complete has the complete information about the expansion history of the universe, and we would like to now get some feeling about the solutions. Now, before going into a discussion of the solutions, let me just then tell you what is the whole philosophy of this approach. So, in this approach, we or in general we would like to ask the question, what are the components of our universe? What is the expansion history of our universe? How did it expand? How is the universe expanding? What was the past of our universe? Now, in this approach, this whole thing is quantified in terms of the present values of the density parameters. So, the whole of determining the expansion history of our universe boils down to determining the density parameters for these various constituents that make up our universe. Now, we will consider the simplest possible situation, one of the simplest possible situation that is consistent with current observations. This will require us to consider four different components of the universe. The first component, let me enumerate them, tell you some of their properties, and then we shall go ahead. So, the first thing that we shall have to consider is the usual matter which has no pressure equal to 0, which is also referred to as dust. So, for this component of the universe, we shall denote this component by the subscript m. This component has no pressure. So, W, the parameter W, has a value 0. And we have already worked out a solution where we only have this component. We have discussed this to some extent in previous lectures, and we have worked out one solution where there is only this component. Now, the density of this component scales as a to the power minus 3, W is 0, and this is equal to the next component that we are going to be we will include in our model is the relativistic particles. Photons, neutrinos, these are relativistic particles, and we shall also be referring to this as radiation. So, this component describes a situation where our universe is filled with radiation, and this component has pressure 1/3 rho c square. We shall denote this component by a subscript r. So, W r is 1/3, and we have seen that rho r a to the power 4 is a constant. The third component that we shall be dealing with is the curvature. The curvature component we have seen requires the rho curvature a square to be a constant. So, this is equal to rho curvature naught. W curvature is minus 1/3, it has a negative pressure. The pressure is minus 1/3 rho curvature c squared. And I have told you that this is not really some constituent of the universe, it is a fictitious component that we have introduced to, so that we can think of, so that we can treat the constant of integration in the same footing as all the other constituents of the universe. The fourth constituent, the fourth component that we shall consider is the cosmological constant. Now, what is this cosmological constant? It is something absolutely new for us. We have not encountered it earlier. In Einstein's theory of general relativity, there is the Einstein's theory of general relativity admits the possibility of such a constant called the cosmological constant. Now, if you want to interpret it in the Newtonian framework, which we have adopted, if you want to interpret, so the cosmological constant appears as a constant in Einstein's theory of general relativity, and the theory admits the possibility of there being such a constant. We shall discuss it later. If you want to interpret this constant in this Newtonian framework which we have adopted, we can think of it as some kind of material that fills the universe, which has got negative pressure, whose pressure, so we shall refer to this as lambda. So, we can think of it as some kind of a component of the universe whose pressure is exactly equal to minus rho into c square. So, this is a component of the universe which has a pressure which is exactly equal to the negative of the energy density. So, W lambda is minus 1. So, remember, it appears as a constant in Einstein's general theory of relativity, but we can, for our purposes in this Newtonian framework, we can think of it as some kind of material that fills the whole universe, which has a very strange property that its pressure is minus the energy density. So, W is lambda is minus 1. Now, remember that as the universe expands, the energy density, the density into a to the power of 3 into 1 plus W, this term remains a constant. So, for the cosmological constant 1 plus W, W is minus 1. So, this whole thing becomes, the exponent becomes a 0, and we have the fact that we are led to the consequence that the density of this component remains unchanged with the expansion of the universe. So, this density rho lambda is equal to rho lambda naught. So, with the expansion of the universe, this density does not change. So, in Einstein's theory, it appears as a constant. In our Newtonian interpretation, it appears as some material whose pressure is exactly negative of the energy density, and as the universe expands, its density does not change. Now, you may find it, you may be wondering, why does not the density of this material change as the universe expands? For example, for the usual matter, when the universe expands, its density falls as 1 by a cube, conservation of mass. Now, we have seen, let me explain to you in this Newtonian framework why the density of the cosmological constant does not change. We have seen that the quantity to look at is the conservation of energy, first law of thermodynamics, when you are dealing with material that has got pressure. Now, if I take a gas which has positive pressure and expand it, the gas does work on the boundaries. The gas does work which causes the internal energy to fall faster than it would have done if the pressure was 0. Now, positive energy, the gas does work. So, when there is negative energy, the gas gains energy, the expansion does work on the gas, and when the pressure is equal to minus the energy density, this work done is exactly compensates for the fall in the energy density due to the expansion, so that finally the energy density remains a constant as the universe expands. So, we will be dealing with 4 kinds of constituents. We have the matter, pressureless dust. Now, I should point out that the dark matter which we discussed falls in this category, is believed to fall in this category. We believe that the dark matter has negligible pressure and it falls in this category. Then we have relativistic particles, radiation, neutrinos all fall in this class. We shall refer to it as radiation in general, not in general, but throughout this. Quite often we shall refer to it as radiation. Then we have parameterized the curvature as a constituent of the universe, and finally we have the cosmological constant. Now, there is a component of the universe called the dark energy, which I have possibly mentioned earlier. The cosmological constant is one possible explanation for what we see as what we refer to as the dark energy. There are other possibilities. It may be possible that the universe has some kind of material, maybe a scalar field, some kind of constituent, maybe a real constituent like a scalar field, which fills the universe, which actually has P is equal to minus rho c square. So, there is a possibility that there is a constituent of the universe which has got substantial negative pressure, which is not the cosmological constant. So, the cosmological constant is one possibility. So, the cosmological constant is one possibility. There is a generic term dark energy which is used to describe such a constituent of the universe, which may also be a cosmological constant. So, the dark energy is a more general kind of term referring to a constant of the universe which has negative pressure. The cosmological constant is one example, and for our lectures we shall mainly be focusing on the cosmological constant as the dark energy, and I have told you what we mean by the cosmological constant. You could bear in mind that it need not be the cosmological constant which is the dark energy. There may be some other component, some other kind of thing which has the same kind of property where there is substantial amount of dark energy that is negative pressure, substantial negative pressure. Now, so we are going to be dealing with an universe which has these 4 components, and each of these component is quantified by the respective density parameter, the value of the respective density parameter at present. So, the matter is going to be quantified by omega matter naught. It tells you what fraction of the critical density is at present in the form of matter. Then we have the radiation. So, omega relativistic particles are naught. We have the curvature omega k naught, and we have the cosmological constant omega lambda naught. And we have the requirement that the total sum of these 4 omega matter naught plus omega radiation naught plus omega curvature naught plus omega cosmological constant naught. This is a constant, so this does not change. This should be equal to 1. So, the sum of these 4, in our model we have only 4 possible constituents. So, the sum of these 4 should be equal to unity. So, we would now like we would now like to write down the equation governing the expansion history of the universe in a model where we have all 4 of these. So, let us do that. So, the equation is h square t So, this is the equation that I am writing down, and for each component this exponent is going to be different. For radiation W is 1/3. So, if W is 1/3, this exponent becomes -4. Then for the matter, it is omega matter naught a to the power -3 plus omega curvature naught a minus 2 plus omega lambda naught. So, this is the equation that we wish to solve. And if you really want to specify the cosmological model corresponding to our universe, so we are assuming that our universe has only these 4 components, and if you really want to specify what is the cosmological model corresponding to our universe, then what has to be done is the value of H naught has to be given and the value of these 4 parameters have to be given. Once these values are given, once these 5 parameters, the value of these 5 parameters have been given, the expansion history can be completely worked out, because we know we have to integrate, just integrate this equation. You know the Hubble parameter at all instants of time, and from here you can work out the scale factor at all instants of time. Now, what I am going to do first is I am going to take up each of these components individually. So, let me first consider the situation where my universe has only radiation. Let us consider a situation where my universe is dominated by radiation. Now, before going into solving this, let us ask the question, what is the relative importance of these 4 terms? What is the relative importance of these 4 terms? Now, you can see that this term has the scale factor to the power of -4. This term has a scale factor -3, this has scale factor -2, and this has no power of the scale factor at all. So, what you can say from this is that when the scale factor is small, this term is going to be the most dominant term, and then as the universe expands, the scale factor increases, this term is going to lose out to this term, and then this, and then this. So, I can make a diagram log rho versus log A. The cosmological constant density remains a constant. So, for the lambda it is going to look like this, and then the curvature density falls as a to the power -2. So, that is going to fall something like this. This is the curvature, and the matter density falls as a to the power -3. So, that is going to fall something like this, and the radiation is the steepest fall. So, it is going to fall something like this. So, this is radiation, this is matter, this is curvature, and this is the cosmological constant. So, at very small values of the scale factor, when the universe is extremely small, we are going to have a radiation dominated universe. The radiation term is going to dominate, and then there will come a time when the universe becomes matter dominated, and then there will be a time when the universe becomes curvature dominated, and then cosmological constant dominated. So, the exact epochs when these transitions take place will depend on the value of these different density parameters, will depend on these values, which is something we shall discuss. But the point to bear in mind is that early in the universe, when the scale factor is extremely small, it is this term that is going to dominate, then there will be a transition here, here and here. So, let me work out now the solution taking only one term into consideration at a time. So, suppose the universe is dominated by this term, what is the expansion going to look like? So, this is the radiation dominated universe. So, we are going to neglect the effect of all the other terms to the dynamics and consider only the radiation term. So, what we have, the left hand side is A dot by A squared is equal to H naught omega radiation naught into A to the power minus 4. So, what we do is we take this equation, the equation that governs the dynamics of the expansion history of the universe, where we have neglected matter, curvature and the cosmological constant, only radiation. So, early in the universe, when this term, when this component dominates, we can neglect all the other terms and this is what we have. So, when the universe is radiation dominated, it is governed, its expansion is governed by this. So, we can take the square root and what we get is A dot is d, or we can write, A dot is equal to, so I am taking the square root of this, then I am going to multiply it by A. So, after taking the square root, if I multiply by A, I have A to the power minus 2 into A. So, what I have is H naught omega radiation naught square root into A to the power of minus 1. Or what this gives us is I can take this A to the power minus 1 onto that side. Basically, I can multiply it throughout by A. So, what I have is A dA is equal to square root of H naught omega radiation naught into dt. So, if I integrate both the left and right hand side, what I get is A square is equal to, so there will be a factor of half which I can take on the right hand side, 2 root H naught omega r naught to the power of 2 into t. So, finally, what we have is that A t is equal to 2 to the power half H naught omega radiation naught to the power 1/4 t to the power of half. So, the point to note over here is that in a radiation dominated universe, the expansion of the universe goes as t to the power half. Now, let us work out the Hubble parameter. How does the Hubble parameter scale with time in this particular cosmological scenario situation where the universe is radiation dominated? The Hubble parameter h of t is A dot by A, and this A is a constant into t to the power half. So, when I differentiate this, I will get half times that constant which I am calling c, t to the power minus half, divided by c into t to the power half. I am writing A as c into t to the power half. Finally, I have the fact that the Hubble parameter is half of 1 by t, or t the age of the universe is half the Hubble parameter. So, this is the radiation dominated model. Let me next take up the matter dominated model. In the matter dominated model, which has been discussed already, let me just repeat it again. So, if we consider the matter dominated model, we are going to ignore this term and this term. There is only matter, nothing else, that is the dominating term. So, what we get is A dot by A is equal to H naught to the power of half. I am taking the square root of the H naught into omega matter naught to the power half. So, I am taking the square root of the right hand side, omega matter naught to the power half, A to the power minus 3 by 2. And I have A to the power minus 1 on this side. So, I can multiply it by A to the power A, I multiply this with A, and I am led to the condition that A naught is equal to H naught square root of omega naught into A to the power of half. Okay, so we have to integrate this equation to determine the expansion of the scale factor in the matter dominated model. Time is running out, so let me stop here and resume from this point in the next class.